It is a plane, and it's flying. But how? And what's keeping it from not flying? Well, that's what I'm going to answer in this video. Yeah, that's not how planes work. If only though. There's actually a lot more science and engineering that goes into aircraft than you might think. And it's not like they just magically defy gravity. Nope. They still have forces acting on them. Four of them, actually. We call these the four forces. So, these forces are gravity, drag, thrust, and the force. Just kidding, that last one was actually lift. So, how do these forces work? Well, we'll start off with gravity. And if you haven't heard of this, you've probably been living under a rock. Because of gravity. But in aeronautics, there's a little bit more to it. Well, there's this thing called the center of gravity, and it's the center of all the weight distributed in the plane. It's like when you finally perfectly balance a pencil on your finger. The center of gravity is where you're holding that pencil from. The center of all the gravity. So it's the balancing point, and placement relative to other forces can determine how much of that force turns into rotation, which can be counteracted with flight controls. Kinda like how this pencil keeps wanting to fall over. Wait, I can counteract it with my finger. And now this pencil can fly. Not again. Okay, maybe we're not quite there yet. So, we did gravity, but what about drag? Well, the air hits stuff. Thanks for watching. Wait a second, this video isn't over yet. So drag is what you get when the air opposes the plane's forward movement. The air molecules are pushed forward by the plane, also pushing the plane back. This builds up pressure on the surfaces hitting the air. Well, now what? It's not like the air just hangs out there. Hey, what's up? Nothing much, how about you? Oh, I went to 30,000 feet yesterday. It was really cool. Oh yeah, really? Yeah, I caught a thermal. Oh yeah, that reminds me. I went through the thickest storm yesterday. Oh yeah, how big was it? Oh, it was huge. Nice. So the air doesn't just stay there because of the high pressure and density. So it goes outward and around. The air still tries to keep going forward, building pressure. But it can't because, well, there's a wall. But being squeezed up against it increases density, which pushes incoming air away. So, what's happening behind the wall? It's not like it leaves a trail of no air. Nope. Well, air likes to follow the shape of objects, kinda like water. But this air can't, cause there's a wall. And it can't just take a 90-degree turn and keep going, not at these speeds at least. And the wall builds up a lot of low pressure behind it. But what the air does to fill this up is it completely stops in its tracks, goes backwards, and then a lot of it does the same thing again, creating even more drag. Wait, what's that? Well, eventually these two sides of air start contradicting and smashing into each other, and this makes what are called vortices. And these vortices create kind of a buffet effect, and even more drag. Thankfully though, some shapes can be more aerodynamic than others. This one's more curved at the front and streamlined at the back so the air can flow more smoothly around it. And all of that was called form drag. But wait, there's more. There's also a thing called skin friction drag. And it's exactly what it sounds like, drag caused by air friction on the surface of the plane. And rougher surfaces cause more skin friction drag than smooth surfaces. And I hate to break it to you, but that magic carpet's gonna cause a lot of skin friction drag. Alright, one more thing. Just bear with me. Well, there's this thing called induced drag. So lift isn't always perfect. Sometimes the plane has to be angled in order to generate enough lift for the desired flight. More about this later. By angling the wings, the lift from those wings gets thrown back a little. But wait a minute. Wouldn't that pull the plane back? Well, that's where induced drag comes in. It's sort of like a side effect of lift. And the more the plane is angled, the more lift and induced drag you get. But there is a tipping point. And this is called a stall. In a stall, the wing is angled so much that it becomes more like the wall from earlier, and creates more drag and less lift. Also, the faster you're plane, the less induced drag you get. Since lift increases with speed, the plane doesn't have to angle as much to get the same amount of lift. You do get more form and skin friction drag though, because the air is coming at you faster. There's sort of a middle ground here though, where the combined drag is the least, and this will give your plane the best performance and lift to drag ratio. In this case it's around 80 knots, or nautical miles per hour, but it can vary from plane to plane. And that's about it for drag. So we did drag, but what about lift? Well, lift is generated by the wings on a plane. Smaller amounts of it can be generated on other surfaces, but mostly the wings. But how? Well, wings generate lift because of the way they are. Hope you enjoyed! So we did lift, but what about... Wait, something's not right here. So most wings follow the same basic shape, and this is called an airfoil. Because of this airfoil shape, it generates lift. And there are two theories that explain this, which are Bernoulli's principle and Newton's laws. Some people say it's because of Bernoulli's principle. It basically says that faster moving air has less pressure than slower moving air. That much is true. Kind of. Well, first let's just try and see what on earth that means. So what about that pressure part? And pressure is a thing that's misunderstood sometimes. Pressure is the amount of force the air exerts, not the density. The density is the density. But pressure and density relate pretty closely. So air with high density tends to create more pressure than air with low density. That pressure difference causes it to expand outwards. So if there's high pressure below a wing and low pressure above it, then it should go up, creating, wait for it, lift. Well, what causes that low and high pressure? What some people say happens is that the air moves faster on the top of the wing than on the bottom. But why? Well, it's because of the shape of the airfoil. If both sides of air come towards the wing at the same point and have to leave at the same point, then the top air has to travel faster to get around the curve. And this is called equal transit. Makes sense, right? Only problem is, it makes no sense. Because that would mean that planes can't fly upside down. And there's no reason for two sides of air to be stuck together like that. Studies have found that the top air actually reaches the trailing edge of the wing before the bottom air. So what is happening here? Well, let's take a look at the other theory. Newton's laws of motion. Specifically Newton's third law. Yes, it's a trilogy. So Newton's third law says that every action has an equal and opposite reaction. Now you might be thinking, every react equal what? And that's exactly what I was thinking. Just kidding, I can explain it. So basically what that means is that any action performed by an object, like a wing, or a pillow pet, or a box of tissues, always comes with some other action with equal force and in the opposite direction when it happens. This is what makes rocket engines work. The chemical reaction spewing out the engine push the rocket in the opposite direction, and with equal force. This is also why stubbing your toe hurts. Now you might be thinking, hey, why doesn't that wall move when you stub your toe on it? So much for equal and opposite reactions. And that's where we get to Newton's second law. You see, that wall is stuck to the Earth, and the Earth is huge. And Newton's second law basically says that objects with more mass, or stuff, are harder to accelerate than objects with low mass. One second, I gotta zoom in. There we go. Also, the more force you put on an object, the more it will accelerate as well, which makes a lot of sense. So Newton's second law is why you usually don't see propeller planes with rocket engines, and also why huge airliners don't get rocked around in turbulence as much as lighter aircraft. Okay, well what does this have to do with lift? Well, as the top air comes towards the wing, it follows its shape, and as it follows this curve, it starts to go down, and it keeps doing that for a while after it's gone past the wing. The bottom air is also occurred by the stream of falling air above. Wait a second, Newton's third law works here. By pushing the air down, the wing is pushed up. This also explains why you have more lift at higher angles of attack. If you have the wing angled, the air has to go down more in order to follow its shape, also resulting in more upward force, lift. It's also good to keep in mind that not all the lift is generated at the trailing edge. Sure, that's where the air leaves the wing at a downward angle, but the air goes down gradually at other areas of the wing to result in that. Alright, looks like my job's done here. Hope you enjoyed. Wait, what about Bernoulli's principle then? That experiment showed that the air did move faster at the top of the wing. So, does Bernoulli's principle work or not? Well, yes, the principle itself works, but equal transit doesn't, because the principle was originally intended for stuff like enclosed tubes, where the air goes faster and creates less pressure in more narrow areas, not wings. But there is a pressure difference and the air is faster at the top of the wing. It just works in a slightly different way. So as the top and bottom air splits at the leading edge, there's an initial curve upwards, and it's thrown around the top of the wing. The bottom air is squeezed against the bottom of the wing, and how much those two things happen depends on your angle of attack. And this is where the pressure comes in. If that bottom air is directly hitting the wing, pressure is created, which pushes the wing up and backwards, creating lift and induced drag. It also slows the air and pushes it down. Now for what the top air does. And we'll also get into how that curving works and why the air goes faster. So if air didn't follow the shape of things, there would just be a bunch of no pressure above the wing. But that's obviously not the case, and that's because air pressure also acts on other air. So if there's higher pressure above the curve than below it, then any air molecules will want to go towards the wing. And since the curve of the wing is constantly trying to block the air, incoming air will just keep going down in order to fill the lower pressure areas. And this creates what's called the Coanda effect. So if you have an air molecule going into that low pressure zone, it will be pushed forward by the higher pressure behind it and accelerate. So both Newton's laws and some fluid dynamics can be used to describe how lift works. So I hope I've lifted your spirits with that one. Because trust me, this is going to be so... Okay, I'll stop now. So thrust is what propels the plane forward in order to have enough speed to produce lift. It's usually generated by some type of engine. There are two main types of engines used in aviation, and those are propeller engines and jet engines. There is a rocket engine on the X-15 though. It's pretty cool. So propeller engines are usually found on smaller planes like this one, or this one. And they typically don't generate as much thrust as jet engines, but they get the job done, and in a pretty simple way. So propeller blades are shaped in a really similar way to wings, and that's basically what they are. Spinning wings that produce forward lift in the form of thrust. Kinda like a ceiling fan. Oh no, my ceiling fan is a propeller now. So by propelling the air backwards like a wing would propel the air downwards, the plane is pushed forward. And the same principles that act on a wing also apply to a propeller. The more angle of attack the blade has, the more thrust is generated. But more power from the engine is needed in order to resist an increase in induced drag. Alright, now for jet engines. There are a few different types of jet engines, but the most common one is a turbofan engine, found on most modern airliners. So here's how they work. And to explain it, here's a picture of the inside of one. Okay, maybe it's a little intimidating, but the idea is actually pretty simple, and it can be divided into sections. The whole goal here is to get a jet of speeding air out of it. So like a propeller, the whole thing spins. And it looks pretty cool too. So that giant fan at the front of the engine is what initially sucks the air into the inside. Some of it goes around the other components, and some shoots straight through them. That air's next step is going through a series of compressors, which increase the pressure of that air, making it want to expand. After that, it's burned with fuel in the combustion chamber, increasing its temperature and pressure even more, before shooting out backwards and spinning the turbine that drives the engine's rotation. And then after that, it blasts out of the engine through the nozzle. Oh, and remember that air that went past the other components? That's called bypass air. And it helps reduce noise as it mixes with the high-pressure jet, and actually accounts for the majority of the thrust. Turbojet engines work in basically the same way, but without the bypass air, and ramjets are jet engines that don't use a fan or any moving parts, but instead ram incoming air into the engine and ignite it with fuel. There are also turboprop engines, which are basically propeller blades spun by turbojets. The intake air and fuel are what drive the rotation, while the propeller turns that into thrust and sucks more air in. So we did thrust, but what about... Oh, we're done. Mission accomplished. So all these four forces, when used correctly, allow planes to do what they do in their own awesome ways. In order to take off or climb, the lift generated by the plane needs to be stronger than the gravity. And the placement of those two forces also affect how the plane flies in general. And in order to generate lift, you need airspeed, which you can get by using thrust, and sometimes gravity. And balancing it with drag in order to get the best performance out of your plane. So what are you waiting for? Go fly a plane or something. I'm just kidding, don't do that until you have the proper training. No reason not to learn though. So I hope you enjoyed, and I hope you learned something in this video. Bye!
This has been a Cademan Branch production. We hope you learned a ton, and we hope you enjoyed it. This video was created, written, narrated, animated, edited, and produced by Cademan Branch.